Hello everyone. I want to welcome you all today in this uh, video. Today we are going to learn about um, verifying inverse square law and to study the photoelectric effect in a photocell and how to derive a Planck's constant in our physics practical lab. So without any consuming time, okay, I want to move towards my slide which I have prepared. Okay. Um, right now, we are here, and our main aim is to determine a Planck's constant and verify a inverse square law. Okay, Planck's constant, we all know, okay, its value is 6.64 into 10 to the power minus 34 joule second. For this, we need this type of instrument, okay, Planck's constant measuring instrument available in our physics practical lab. I want to say about the working mechanism and the thing, okay, which we need, how this experiment works, how this instrument works. Okay, I want to go through little bit detail in this. Here it is. This is a Planck's constant measuring instrument. Here is a light source. Okay. uh, Whenever you turn on the switch, the light emits from the light source, and this is a small hole, and inside there is a photocell. Okay, when the light hits the photocell, then electron can be ejected in a circuit, and the circuit detects a current. And when there is a slide button over here. When you take this slide to the other side, it will measure current, and current will be displayed over here. And whenever you take this black color to the other side, it will measure voltage, and voltage will be delivered over here. Okay. Voltage will be delivered in volt, and the current will be delivered in um, micro ampere. Okay. Um, okay. Here is the ratio, conversion ratio, at what ratio you need this voltage and current. And this is the intensity of light. When you rotate it clockwise, then the light intensity will be higher. Okay, higher intensity light will be allowed to go inside this. And this is the experimental circuit. And this is the voltage direction, whether you want to give a negative reverse voltage or forward voltage. Okay, and this is the voltage adjuster, and this is the indicator of this instrument. It is not working over here. It should be glow red in color, and here is on and off. Okay, this is the simple instrument, and here is the scale, okay, of measuring at what distance we are keeping this light source. Okay, this is the thing, and I hope you can see this filter. Okay, here are different color filter: red, yellow, green, blue. Okay, this filter we use over here, and we only pass those wavelength of light which we prefer. Okay, so uh, there are different filter. We need to remove this and keep the other one: red color one, green color one, yellow color one. And for that, we need to study a different data. Okay. Uh, Now after this is the experimental circuit of a photoelectric effect. So we need to get this type of plot of frequency and stopping potential. I will tell you how to derive this type of curve. And after that, we need to know, as I told you, we use a different color filter over here. Different color filter have a different value of wavelength. So different value of wavelength, it should be given to us. So it is mentioned on that filter only. So if you are using a red color filter, then lambda r will be 635 nanometer. You can convert this by multiplying into 10 to the power minus 9 and convert it into meter. Okay, similarly for yellow 1 and yellow 2, there are two different wavelength for yellow color, which was provided for us. You can be provided any color. Its wavelength is already mentioned on that. So there is no any kind of trouble. And for that, as we know the wavelength of different color of light, we need to get the frequency, because we want a relation between frequency and stopping potential. Okay, I will tell you how to get the frequency. Frequency is equal to c by lambda. C means the velocity of light, 3 into 10 to the power 8 meter per second, and lambda, you know, you convert this into meter, as I told you, multiply by 10 to the power minus 9 and get your respective frequency. And from the calculation we'll get a stopping potential for the different color. So I will tell you for the red color how to determine this. For this we need to move towards our this experiment. You set this light intensity at any point 30 centimeter for an example. You keep a red color filter over here and you want to measure a current. Okay, set a little bit light density intensity and get a current. Okay, and after that you give the voltage direction to the negative one. And as you know that there is a red color filter, light source intensity is sufficient to hit and eject the electron. So we are getting a current. Electron is being ejected in a circuit. This circuit, okay, when the light source comes here, it will be ejected, electron ejects from here to here, and circuit will be completed, and there is a detection of current. Okay, we know the current will be detected in this circuit. So now we'll give a reverse bias voltage, and voltage direction will be negative. Okay, we'll give suppose here is a current, suppose a current of 1 microampere. Okay, suppose a current of 1 microampere or 1.09 microampere is the reading which is displayed for the red color filter. So after that, what we'll do, we'll give a voltage direction reverse. We'll reverse the voltage and we'll increase, we'll adjust this voltage adjuster. Okay, we'll adjust in such a way that we are giving a reverse bias, opposing voltage we are giving, so that this ejected current should be minimum, that is equal to 0. So at what voltage you set up over here, the current will be 0. You leave this at the same time when the current will be 0. This is keeping fixed. Okay, the light source is keeping fixed. So at that time we want to see the voltage. Okay, so immediately you turn on this black colored switch to the other side, and the voltage will be displayed over here. That is the stopping potential for the same intensity of light, that is the red colored light, for ejecting the electron. Okay, although the red color light eject electron, okay, there is some certain value of current which was mentioned before. So when we reverse bias the voltage, then the current will not flow in the circuit, because whatever the voltage we are giving here, that is called the stopping voltage, because we are stopping the current with that voltage. So that is called a stopping potential. So I want to move forward. By that way, we have got the value of stopping potential for red filter is 0.24 volt. It will be displayed whenever you turn that switch to the other side. Or similarly for yellow 1, yellow 2, green filter, blue filter. So after this, we have a formula for measuring a Planck's constant between red and yellow. See here, first one red and second one yellow. We'll see the Planck's constant between red and yellow 1 filter. This is the formula E. Okay, Planck's constant for red and yellow one. E Byi minus Br. Okay, lambda r minus lambda yi multiplying by lambda r into lambda yi. Okay, this is the formula. E means the value of electron, that is 1.6 into 10 to the power minus 19 coulomb. C means the speed of light. B means Byi, we know from here, okay, yellow one. And Br means for the red, stopping potential for red. B means for the potential. Okay, so you apply this formula over here and you get your answer. Okay, although the answer is not correct because it is practical, there may be certain error. So similarly, you will get for red and yellow one and yellow two and green and blue. You need to change the value for this. Okay, if you are using for red and yellow one, then red will be on yellow one minus red by lambda r minus lambda y1. Okay, you adjust this value and get for the different one, and you need to analyze the error. Similarly, here yellow one in green filter, okay, you need to get this value. Okay, similarly for other, I haven't kept. So we have got a stopping potential and we know the frequency for different color light. As we know the lambda wavelength, I told you that the frequency can be got from here. We know the lambda, we know value of C, okay, frequency for different color light. And we know the stopping potential for the different colored light. Okay, so we plot the graph between these two, we take out a slope and we measure a value. Okay, it is nothing harder. Okay, it is not very much hard. So another one is to verification of inverse square law. Okay, for the verification of inverse square law, what we will do is we will come again to this experiment in our next step. So now we'll set up the voltage direction positive, we measure the current, okay? And we take any filter which we want, okay? I have taken here a blue and red filter. So for that red filter, you move this light source. And we know that whenever the light source will be near, the intensity will be increased and the current will be increased. Whenever the light source will be far, okay, now we'll not do anything. We measure current. This will be in positive because we will not give reverse bias voltage. Okay, if you give reverse bias voltage, current may be zero. So we'll give forward bias voltage. So for that, we'll give the voltage direction positive. We move this light source. As we know, when the light source increases, intensity of light source increases, the ejecting electron also increases from here, and the more current will flow in the circuit. So if you move the light source from here and there, okay, if you move near, current increases. If you take far, current decreases because the intensity increases. So this is the only concept. We need to sketch a graph for this and we call it as an inverse square law. Why the word inverse is here? Okay, let us see. Okay. Okay, you see here, as the distance decreases, okay, then the current increases. And as the distance increases, then the current decreases. So that's why we call it as an inverse square law. So I have a data over here. Okay, for the two colored filter, you can see here verification of inverse square law. Okay, this is the verification of inverse square law. This is a serial number and distance between lamp and photocell. You know there is a measuring scale. You need to move that lamp and at what position the lamp is at that time you need to get the value of this blue filter. So we'll see here for the 18 centimeter distance. Okay, we are getting the value of current 1. For blue filter only I'm talking, okay? You see only these two things. If you know the value of R, you know this value, okay? So for 20, okay, it is same. 18 and 20, there is no change in current. If you increase the distance, current starts, okay, sorry, if you increase the distance, then actually current should start decreasing, but this one value, you neglect this one, okay? There may be some error. If you go directly from 20 to 24, okay, then, okay, this my data is a little bit wrong. Let us see for the red color filter, okay? For 18, you know the value of current is 1.6 microampere, okay? And for 20, you have got the value of 1.380. This one is a little bit mistake that setting one multiplication term, there is one button over here. Due to this button, I could not get the correct data. I hope so. This one. There is a multiplication term. But we get our data. So for the red color field, any one you can take or any two which you like. Don't use for all the thing. It comes, the nature of graph is same. So for 18, value of current is more. As the distance increases, value of current starts decreasing. See here, 0.578. This you know, okay? You just need to move that lamp and notice the value. So for that, if you place the graph between 1 by r square and this red color current, okay? If you take this 1 by r square in the power minus 3 centimeter square over here and the current, you will get this type of nature of curve. So this is the verification of inverse square law. And we know the value of Planck constant over here, okay, from this formula. We know the value of Planck's constant. So this is the formula to be that we need. So from here we are clear about the determination of Planck's constant and verification of inverse square law. So after saying this much, I want to conclude my video. Okay, I want to say you thank you very much for watching this video. If you have a valuable comment, so please don't forget to comment over there in the comment section. Okay, have a nice day. Bye bye.